Hi, I'm Dr. Chris Creighton, and we're going to be talking about graphing exponential functions. The core objective here is taking an equation for an exponential function and then graphing it. So determining if an equation or a graph is exponential, and then finding the domain, range, intercepts, asymptotes of exponential functions. And then this will let us get into solving exponential equations and eventually getting to logarithms. So we're going to get started by graphing f of x is equal to 2 to the x. So this is an example of an exponential function where the variable is in the power. So this is 2 to the x. So your variable is in the exponent. And then the 2 is what we call our base. So we choose the values of the exponent for these functions. So for example, f of x is equal to 2 to the x. So we're going to pick exponents. So I'm going to just do the standard -2, -1, 0, 1, and 2. So these are some nice values of x to exponentiate. So for example here, this will correlate to 2 to the -2, which is equal to 1 over 2 squared, which is equal to 1 over 4. 2 to the -1 is equal to 1 over 2. 2 to the 0, anything to the 0 power is always equal to 1. 2 to the 1, well that's just 2. And then 2 squared, well that's just 4. So this gives us a total number of 5 points. So here at -2, we're at a 4, so we're like all the way down there. At -1, we're at a half, so we're right there. At 0, we're at 1. At 1, we are at 2. So while this looks sort of linear, it is in fact not. It's bending a little bit, which you'll start to see here. So at 2, we're all the way up here at 4. So you can start to see that bend a lot more now. And in fact, you can pick it up even more if I plug in 3, because that's 2 cubed, which skyrockets all the way up to 8. So now up here at 3, we're all the way up there at 8. So we get the exponential function looking like this. But what happens if I were to keep plugging in negative numbers? So like for instance, if I plug in -3, this is 2 to the -3, which I'm going to go a little faster, and it's 1 over 8. So that is even smaller right there. -4, well that's 2 to the -4, which is equal to 1 over 16. So that's even smaller there. So like this thing like flattens out quite a bit there. It does not cross the axis, but it's really hard to not draw that. But it gets really, really close to the axis. So I'm going to point out a bunch of key features with this. So the first thing here is the domain is anything. You can plug in any number here to this. For example, I can plug in the value of 1/2. This is 2 to the 1/2, which is whatever the value of the square root of 2 is. That's a perfectly fine value to plug in. I'm picking nicer numbers here because I'm exponentiating and doing this by hand. Next, the range. The range is 0 to infinity. There's no number you can plug in to get 2 to the x being equal to 0. So this is due to 2 to the x is equal to 0 has no solutions. There's no way to specify when that's 0, so that thing is 0. And 2 to the x is always going to be some positive number. All right, it can never be 0, so I said that this thing is always positive, and so no matter what I plug in, this is going to be positive. 2 to anything is going to be a positive number. And so this gives us this nice property here, where there's this thing called an asymptote, which means that the function gets arbitrarily close to this. So there's a horizontal asymptote. And this is at y is equal to 0. And what this means is that out here, when we're down here at like -6 or -8, or even if we keep going with farther and farther negative numbers, the value of the function gets arbitrarily close to 0, which is why it's y is equal to 0, but it never hits 0 because there's no solutions to 2 to the x is equal to 0. That's what a horizontal asymptote is. And then so from this we see that there's no x-intercept. It never crosses the x-axis, and our y-intercept is in fact right there. So our y-intercept is the point 0, 1. And the next thing you can kind of see here is that this thing looks like it's going up. I'll call this increasing. So we get a bunch of properties from being able to graph this thing. And you notice I did this by just choosing enough numbers to get enough data. When you're graphing these things, you do need to encompass all of the data, or choose numbers that encompasses all the data the function gives you, like domain, the range, the horizontal asymptote, and then the intercepts. Here we have another exponential function. Again, this is an exponential function because it is some number to an exponent that has a variable in it. In fact, the exponent's x plus 1, so this is 1/2 to the x plus 1 power. So again, we'll start off here by making a table, the basic premise here. So I'll do 1/2 to the x plus 1. I'm going to plug in the same starting values we did before. But like last time, we'll need to pick a couple extra values to encompass all the features. So when I plug in -2, 1/2 to the -2 plus 1, which is equal to 1/2 to the -1, which is equal to 2. So at -2, we have the value 2. -1, I get 1/2 to the -1 plus 1. Well, that's 1/2 to the 0 power, which is just 1. So here at -1, we're now at 1. So you should initially see here that this thing looks like it's going down instead of up, which is in fact the case. Because if we plug in 0 here, 0 plus 1, that's equal to 1/2 to the first power, which is just 1/2. So plugging in 0 to be 1/2 there. Plugging in 1, 1/2 to the 1 plus 1, that is equal to 1/2 squared, which is equal to 1 over 4. So at 1, we're all the way down there already. And then 1 over 2, 2 plus 1, which is equal to 1 over 2 cubed, which is equal to 1 over 8. So here at 2, we're even closer there. So the first thing you should see here is that it looks like this thing is now going down instead of up. So just piecing these components together, we'll pick up some more points. This thing looks like it's decreasing, and that is in fact the case. Next, what is this plus 1 doing? Well, when I plugged in 0, I got 1/2 instead of plugging in 0 getting 1. So that x plus 1, in fact, shifted this over a little bit, which means we need to choose some more points. So for instance, if I choose now a -3, this is now 1/2 to the -3 plus 1, which is equal to 1/2 to the -2, which is equal to 4. So this x plus 1 made this -3 look like you're going to plug in that -2 as an exponent here. So now at -3, we're up at 4. And then at -4, you can check this, we're up at 8. So this thing looks like this. And then it scoots in really close to the x-axis. Doesn't actually cross, but it does. So this is the graph of 1/2 to the x plus 1 power. And the first thing, again, I note is that this thing is now decreasing instead of increasing. It's because the function, as you're going left to right, negative to positive numbers, goes down. It slopes down. So this is a decreasing function. We still have the same domain from -infinity to infinity. The range is, in fact, the same, 0 to infinity. There's no x-intercept for the same reason above. We can't set that thing equal to 0 and be able to figure out what exponent makes something 0. And then our y-intercept is, in fact, 0, 1/2. And that's because when you plug in 0, you get the value 1/2. We also get the horizontal asymptote, which I'll do here in pink, coming across. So dotted and pinked, come across here. So I'm going to label that horizontal asymptote y is equal to 0. And this is decreasing, so it goes from a large number to a small number as you start to plug in things. And so it's now approaching the horizontal asymptote on the right side of the graph. And that is a pretty important feature here. So both of these graphs are of exponential functions. The second one is a slightly modified exponential function, but it's an exponential function nonetheless. The basic idea, we're going to have a function f of x is equal to a. A is called the base. And then the x is called the exponent. And you can identify exponential functions because the base is just a constant number and the exponent is where your variable is. And so for anything like this, the domain is going to be 0 to infinity. Now, if you were to evaluate these on a calculator, so like for instance, if I want to do like f of like 1.3, which is a completely valid input, this is equal to, in this case here, a to the 1.3, but I'm going to go back to the first one, so like 2 to the 1.3 as like an example here. And so the question is, how would you evaluate this on a calculator? We'll come across this a couple times because you honestly can evaluate anything. So there's two versions of keys. So you'll either put in 2 and then the caret key, which looks like an arrow pointing upwards, 1.3, or this will be written as 2, and then your calculator may have a key that says a to the x, and then you'll probably put in a 1.3 there. Or if you hit the a to the x key, it may be like, okay, 2, and then put a little square there, and that you replace with a 1.3. Depends on your calculator. But 2 to the 1.3 power, well, that evaluates nicely to 2.4623, and this is to 4 decimal places. So be careful if there's a problem that says, hey, get to this to so many decimal places, be sure you have the right number. But just to reiterate, you can still plug in any number. So I can do like negative 7.32. So that's equal to 2 to the negative 7.32, which using whichever one of these keys, and you can check this, so 2 to the negative 7.32, well, this is equal to some very tiny number, 0063. Again, this is to 4 decimals. So you can evaluate many of these on a calculator, but again, it has to be some number to any number, all right? The base has to be positive and then not 1. So to reiterate and recap a lot of the properties of f of x is equal to a to x, an exponential function. I always abbreviate this as exponential function. The domain is all real numbers, so negative infinity to infinity, and the range is 0 to infinity, not including 0. That is because we have a horizontal asymptote, y is equal to 0. And the y-intercept is 0, 1, and we do not have an x-intercept. So like sort of I view this one and these three all tied together as highly related to each other. There's a horizontal asymptote at 0. It does not cross the x-axis, so there's no x-intercept, and the range is only positive numbers. And then as we noted, that if a is bigger than 1, so like for instance with the graph of 2 to the x, then f of x is equal to a to the x rises left to right, so increasing. So this thing looks like this. Now if a is between 0 and 1, so like for instance with the graph of 1/2 as a base, this thing falls left to right. So this thing looks like this. And then if we go back and take a look at both of these, f of x is equal to a to x is always 1 to 1, which we will find out that this implies that this is invertible. These are all invertible functions. That is really important because we define the logarithm of a base a of x to be the inverse function of this. So once we get to logarithms, that's where this is coming in.